Uh, okay. Now I'm gonna hopefully should be able to say I'm not sure. Yeah. Okay. Quiz one on module three. And again, yeah, you would have to put. I know the quiz did ask for email addresses, but you don't need to put your email address. Your registration number should be enough for me to check what marks you are. And again, this quiz is not graded. It's only to give me an insight on how well you're doing on the different topics and to give yourselves a revision. Okay, you would have got these questions shuffled, so they may not be the same way that that they're shown here. Actually, wait, me. Okay, now you should see my entire screen. I'm gonna open a new section for this quiz. So quiz one. Okay, question one. I'm gonna have to copy questions. Let me. Okay, the first question. So again, they're not in the order that you would have seen it. You would have seen it in some other order. But the data link layer encapsulates the datagram from the network layer into a dash before sending it into the next node. And the options that are given are segment, datagram, packet, and frame. And this is actually a very simple question because anytime you say the word data link layer, you should know that that data across the network is transferred in the form of frames. So it would have been packet if it was the other layer, the physical layer, but in the data link layer, everything is in frames. So it's not packets. We can just go eliminate each one. It's not datagram. So this is a tricky part. So what this means is it's trying to confuse you with the protocol related to data link layer. It's not a segment. No, we have not come to any of the protocols yet. And so you have a datagram from the network layer and it's encapsulated into what? And that answer is clearly frame. So in this question, frame is going to be the answer. Okay. Let's go to the next question. So let me on the side also fill it up on my screen. Okay. The next question is multicast addresses enable dash communication. So let's new question. So number two, and the question is multicast addresses enable dash communication. And the options are these are very similar options. So it's one to many, one to all, and all to one. Okay. So we know from the name multicast, it has to go to many places. So that definitely eliminates this one to one and all to one. So all to one, even although it has all, you're it's being cast to all. So multicast is saying it's going from one place to many places. So it's not all to one also. Now the two things that you have to take care of is one to many and one to all. So these are confusing options, one to many or one to all. So here's where you need to know two terms, multicast and the word broadcast. And me, okay. When you're talking about broadcast, this is essentially when you, for example, you're broadcasting a TV show, you have one station, TV station, and then it's going to so many different houses. That's a broadcast. But in a network, when you're talking about multicast, let's say you have a ring mesh topology, you have three nodes all interconnected to each other. And okay, let's have a fourth node. Let's have four nodes interconnected, and everything is connected. It's a fully meshed. Yeah. And if this node wants to send it only to this node up here, so you have A and B, that would be a one-to-one connection. But a multicast is when you have multiple. It's there in the name. So you're sending it to two. If this node is sending it to the fourth node also, that will become a broadcast. But it's not. So that eliminates actually one to all because that's what's broadcast. And the answer is one to many. One to many is the answer for the second question. Okay, the third question. This is a question that at least from the review, I see that many people are getting, oops, the third question. Many people are getting this question wrong. Maybe we can discuss this question. Okay. So the question says, the unicast link layer addresses in Ethernet are represented by how many hexadecimal digits separated by colons? So an Ethernet address would be say X, X, and some colon, X, X. So this is how the form is usually. But this doesn't mean that you just have two hexadecimal digits. So the thing is, what you need to ask is, how big is the unicast link layer address? And if you see the length of a MAC address, the length of a MAC address, because so what happens in a link layer is it's basically you have nodes and some one point of information needs to go from one place to another. It's almost similar to how we have MAC addresses in the physical layer. It's not an IP address because you're not sending it across a network. So I think if you know how big a MAC address is, so you can actually check a MAC address. But actually, let me show how to check a MAC address. So if you would just search MAC address, this is what it's going to look like, something like this. And if you can see here, it actually, so here it's quite clear, right? That it has 12 hexadecimal digits. So this is how a unicast link layer address would be. So if you had an option, say for example here 3 or 5, there were no odd number options here, but if they were, you can know that you can immediately delete them. So since here were all odd numbers, you have to know how a MAC address would look like. And the answer here is 12. Okay. Um, so this is what we were, yeah. Okay. So next question. Question 4. Hmm. A burst error occurs when dash number of bits in a data unit change from 0 to 1 or from 1 to 0. I have not checked how many people have got this right. Let me. Okay, so most of you have got this right. So I thought this was a little confusing, but seems it's not. Burst error occurs when dash number of bits in a data unit change from 1 to 0 or from 0 to 1. So a single error, when you have a singular error, it's one bit is changing from 0 to 1, 1 to 0. So that eliminates one. Now the question is whether it's two or more or three or more. So what happens in a burst error is you have, let's say this is the information that is being traveled. So instead of doing this, let me write 1 1 0 1 0 0 0 1. If it was a single error, only one bit will change. So maybe 1 0 0 0 1. This is a single error. When you have more than one, so let's say zero changed, one changed, 0 0 0 one out. So this would be same 1 0 0 0 1. This is a, so you have errors in 2 bits. In 2 bits, this is a burst error when you have more than one. And what if you had three? So 0 1 0, then the remaining 0 0 1 1. This is where you have errors in 3 bits. This is also a burst error. So if you can see the patterns, actually it's more than one number of bits that have a burst error. And so here the answer is, oops, yeah, two or more. Two or more. That's the answer for this question. Okay, let's move on to the next question. Number 5. Okay. If we need to correct two errors, let me paste it. If we need to correct two errors in an 8-bit data unit, we need to consider how many possibilities. This is a little, I think, a little challenging question. So we're given that we have an 8-bit data unit, and there are two errors in it. So let's make an 8-bit. So 1, 2, 3, 4, 1, 2, 3, 4. We have 8 bits of data, and 2 bits out of this 8-bit of data is containing an error. So let's say this and this. These are 2 bits. So how many possibilities are there for these two x's? In how many ways can we choose these two blanks that contain the error among 8? Or in another way, we can say it another way. What combination of these two can be found in these 8? So using the word combination itself, you should know I'm actually talking about 8C2, right? Because yeah, so you're looking at two blanks and 8 spaces. And so how will you choose those two blanks which have the errors in the space of 8? So it's 8C2. And 8C2 means it's 28. How you could calculate, or you could use a calculator. You would do 8 times 7 by 256. Yeah, it's 28. Okay. Okay, so the answer is 28. The correct answer is 28. And it would be wrong to chase 2 because you don't know where in these 8 bits the two errors are going to be. So that's why it's wrong. 28. 256 is a trick. It's a trick. It's a trap. So they want you to think 2 raised to 8. But that would only work if you are checking how many, if instead of how many possibilities, if it was like 0 0 0 1 1 0 1 1. So here you have 4. If it was how many types of error can be there, if you're having 4, then you would have to multiply that by this number, and that will. But here you're only looking at considering the number of units in here. So that's why it's only 28. Okay, that's so the answer here is 28. Here, the thing I didn't fill. So here's 2 or more. This is 12 hexadecimal. Okay, next question. Sixth question. In block coding, messages are divided into blocks known as dash. Okay. So there's not much logic that you have to put in this question because it's it's only asking. So you can see the options here: data words, datagrams, data blocks. Essentially, what they want to know is whether you know what message blocks are divided into. So it's one of these things. And if you remember from the coursework, there is no such thing as data strings. Datagrams, these are messages. These are messages on by itself. These are information that's being passed on the network. It's not a division of blocks. If it was just the messages, you could use datagram, but we're looking at the blocks. And then data blocks, although it seems like it's a block, the correct term for this is data words. So data words is their answer. So this again is you'd have to know that data words and code words, how they work in block coding. So in block coding, what you're looking at, if I can quickly say, if you have a message and you're dividing it into blocks, and each block, so this is a block, yeah. So each of these blocks, so you would have a table that would match the word to the code. So so you have your data words and you would have the corresponding code word. And that's how we can check whether there is errors in the messages using this word and this code word. So this answer is clearly data words. Okay, next question. Seventh question. In block coding, also let's write this as data words. Okay. In block coding, the data word is always encoded as the same algorithm, code word, encryption, message. So this straight from memory, like exactly what we did in the previous question. You should immediately know the answer is code word because algorithm does not make sense. Encryption, it's not encoded into an encryption. Encryption is a process. So you would use encryption to encrypt the data word. But what will you transform it into? So it's going to be a code word. Message is before. So you have message, then data word, then code word. Not so you would encode a message, you would encode a data word into a code word. You would decode it into a data word. And another thing you have to another thing important in this question is always and same. So let me go back to the previous question. In this table, for every unique word that you have in the table, there will be one unique code word. So two words in this code table can have the same code word. So that's the aim of code word to have a specific code. That's this question. Okay, let's go to the next question. 8. Code word. Okay. Now this is a good question about the application of checksum. If the newly calculated checksum at the destination consists of all zeros, the message is dash. So I want to go back and so you have the options accepted, discarded, transferred, and resent. Resent. Okay. I want to go back to yesterday's because yesterday we solved one question on checksum. Yeah, yeah. So what we did in checksum was we added all the individual data points, got a value, took the ones complement and got the checksum. Then when we added the checksum, what happened? When we took the entire thing, added the checksum also. Finally, we got all ones. And following the same procedure, we have to take the ones complement. So, okay, anyway, we have to take the ones complement. And when we took the ones complement, we got all zeros. So, so when we get all zeros, that's when we know that the message was not tampered with. That the message is correct. From the source to destination, the message is correct. So the question was, if the newly calculated checksum, newly calculated means you're using the checksum value and you're adding it to the data. That the destination consists of all zeros. The message is accepted. So this is, if you get all ones, so in hexadecimal it would be FFF and so on, and then when you would convert it, it would all become 000. So instead of the question was if you got all F's in the just in the penultimate step of checksum, what would it be? It would be accepted. Rest of the options discarded is wrong because it's verified. Transferred. So checksum is from source to destination. So there's no transferring that is happening between the nodes. Resend. Resend, it won't be resent if it's wrong. But if it's correct, it won't be resent. Correct, it's accepted. Right? So the answer here is accepted. Okay. Next question. So accepted? Yeah. Next question. Question number 9. Okay. Traditional checksums cannot detect errors when the words are dash and dash by the same amount. So this is a question on limitations of checksum. So let me go back to the checksum that we calculated. Yeah. So what you see here is it doesn't really matter what these numbers are. Whatever these numbers begin, when you add them, you get something. You take the ones complement, you get the checksum. So you can find if you notice, you can actually see a loophole. So let me take two numbers. Let's take a few numbers. Let's say you have data 1 and data 2. And data 1 you have, let's say, the word 1. And here you have the word 2. And when you would add, let's say we're not doing the ones complement or anything. When you add 1 plus 2 in normal decimal, not binary or anything, you'll get 3. And then you would have to, if this was binary, you would have to do ones complement and you'll get the complement. But let's say this was corrupted and became 2. Now what would happen? You get 2 plus 2 equal to 4. So the checksum would not match. You would know that there is some error. But what if both the data was corrected and this became 1? 1. So you can see, so it's going to be 2 plus 1. That is going to give you 3. And you can see here how these are the same. And so what the machine will do, it will give verified. But we know it's not verified. It's not correct because both data 1 and data 2 have been altered. So this is a limitation of checksum. So here the answer would be incremented and decremented respectively by the same amount. So whatever this became, so even if this would increment, if you would have, let's say, so let's increment both by 2. So let this be 3 and this would become 0. Again, the sum would be 3 and the computer would say verified. The node would say verified. The data is verified, correct data. And so the checksum is not sufficient. That's why we learn more methods of error detection and error correction. So this is the answer for the ninth one, incremented and decremented respectively. Okay, next question. Number 10. Byte stuffing avoids issues with flag by adding a special byte called. So this is, you have to know that when we do byte stuffing, we add an escape character. It's not a flag, it's not an end word, it's not an end line, it's an escape character. So you would have data and then you would have an escape character. It's like escape, and there would be another notation, but you would use an escape character and that would show. And then when you'd have the flag, it will not cause problems. So we know where the flag is, and let's say the flag is in between. So this represents this escape character plus flag, would represent that it's not a flag. It's this flag is part of the data. So that's how we use an escape character. Okay. Next, so this is escape. Okay, next question. Slotted aloha reduces the possibility of collisions by dash. Slotted aloha reduces the possibility of collisions by dash by sending by dash then reduces the possibility of collisions by dash the sending time of stations. Maximizing, minimizing, synchronizing, randomizing. So this is quite straightforward because so if you have two nodes in slotted aloha, what happens? There are slots. Let's say 1, 2, 3, 4, and the node can only send at, let's say, 2, and let's say this one can only send at 3. So when through 2 comes in the schedule, this will send, and when 3 comes, the other node will send. Thus there is no collision. If both were sending in 2, this would cause a collision. But since they're in two different places, two different times, you're not. So that's the idea behind slotted aloha. So it's not randomizing that is given. It's nothing to do with maximizing or minimizing. It's all to do with synchronization. So that's the answer for this. Okay, synchronizing. Okay, next question. Okay, CSMA CA aims to dash collisions rather than deal with them after they occur. Again, if you know what the full form of CSMA CA stands for, what the full form is, then you would be able to solve this question because the word CA itself is collision avoidance. Collision avoidance. And so it is going to be, the answer is going to be avoid. It's not detection. That doesn't happen in CSMACA. They don't try to manage a result. So CSMACA carry a sense multiple access collision avoidance. Yeah, that is this answer for the 12th one. Okay, the last question, 13th question. 13. In the stop and wait protocol, if the sender does not receive an acknowledgement within the specified time frame, it assumes that the packet was corrupted and dash it. So what happens in stop and wait? You have a node, you have another node, it's, it sends information, sends data, and then there's an external timer. So let's say that is a time. It sends the data from here and then it waits for the timer. So if the data was accepted, so let's say this is, I'm going to read the information, then what should come back is an acknowledgement. A, C, K. But instead of waiting for the acknowledgement, what it does is it stops and waits. So there is a timer. Let's say it's 3 seconds. It will not be 3 seconds, but for this example, let's say it's 3 seconds. It will wait for 3 seconds to get this acknowledgement. And when it doesn't get in 3 seconds, it'll send another packet. The same, it'll resend that same packet and then wait for the acknowledgement. Then and once 3 seconds get over, the timer finishes, like it'll send, and it doesn't get an acknowledgement. So okay, so it doesn't get, it'll send the data packet again. It'll instead of continuously sending, there's a timer involved. So I said the answer here actually. So if it doesn't get the acknowledgement within the specified time frame, within those 3 seconds, it assumes the packet was corrupted and it resends it. So it does not delay it. It delays. It's the timer that is delaying the packet, not the acknowledgement. It does not forward it. There's no forwarding because it's sending to one. It does not discard. So it's the sender. If it was the receiver, it would discard, but it's the sender. And so it will try and send the packet again. So the answer for this question is resends. Okay, resends. I think we have answered all the questions. So let's submit. And or does it not say? Oh, okay. Oh, okay. Okay. So these are the answers. I think I will enable accuracy the scores to show up for you so you can review. Um, but yeah, this was all in this lesson. Yeah. So what I'm planning to do is, I'm going to stop the recording